All right, cool.
Okay, hello everyone. I'm
Hello,
here with Emmy again.
I'm back.
She was so good last time that she's back again by popular demand. And today we are going to do more quantum computing. That's right. We are simulating a real simulated quantum computer.
Real quantum computer over
So,
this gamified experience. It should
yeah,
be fun.
so this should be
Actually,
fun for anyone who is into quantum computing or who's into cute games.
all who's into physics.
Yeah,
And
so you can share.
me?
Yeah.
All right, cool. Let me do that. So if I can present, share screen.
Mhm.
There we go. And I think now that should work. You can see my screen, right?
Yeah.
Should I have some music?
Yeah.
Right.
The music sounds good.
There we go. Can you hear that?
Yeah, it's good. We need the spookiness to balance out the cuteness. Okay,
There
perfect.
we go.
A little less, a little less.
A little less.
Yeah, that's perfect. Okay.
All right, cool. Fine. So this one is called Not All But Everywhere. So the purpose of this, the aim of this, is to put everything into these fly traps.
Can you turn the music down a little?
Okay, is it really loud for you? Oh no, sorry.
That's good. That's good.
Yeah?
Perfect. That's perfect. Okay.
All right, cool. Didn't realize it was so loud for you.
It comes and it goes, you know? Yeah.
Okay.
It's in a wave.
Function.
So yeah, you were saying.
What was I saying? I was saying, right, the purpose of this, just to remind people who might be watching this, is to get all of these photons detected by these detectors, fly trap detectors.
Yeah.
So once again, we have to fire our photon source and try to get them all detected. So what is this? I'm wondering. These are the mirrors that we can drag and drop.
Are those mirrors or
The beam splitters, aren't they?
splitters?
Non-polarizing beam splitters. So just to remind everyone what that is, it's a slab of glass with a reflective layer. So it looks like the image shown here. And that will partially reflect the beam and then it will transmit the rest of it. So typically, I mean, this is a very normal conventional one, which reflects 50% of the incident light. Let's go and place this somewhere.
Okay.
Where should we place this? We want to get it to hit all the detectors.
This looks too easy based on what we did last time.
It does. I'm wondering if we're going to require a bit more thought later on. Let's try.
Try it.
Oh, okay. Right, that was interesting. So what happens here is it lets through 50% of the light upwards and it lets through the other 50% to the left.
Yeah.
So I guess if we want our solution to go both up and down, we need to change it ever so slightly. How are we going to do that? I wonder if we can superimpose them?
No. That's a good idea though. So it has to go, half of it has to go straight through, and then 1/4 of it has to go to the top, and then 1/8 has to go to the bottom.
Exactly.
So that means, oh yeah, go on.
No, go on.
So I was gonna say, so that means that another 1/8 actually could be going somewhere else.
Exactly.
Yeah.
Exactly. So we're going to probably, given that this is an 1/8, it would probably mean it passes through 2 layers because you have a half times a half, which is a 1/4, and then you'll have a half of that, which is an 1/8.
But I still don't.
So I'm wondering if we reduce the intensity or the impact of this one.
What happens if it goes? What happens if the photon goes through perpendicular to the to there? Yeah. What happens if that happens? Does it reflect back? Because that gives me that's meant perpendicular in the other perpendicular way.
Oh.
Yeah, that way.
Right.
Yeah.
Then only 50% would pass.
Yeah, let's But will it reflect 50% back in the way that it came?
I don't know. That is good. Oh,
Yeah.
yes, right.
Okay.
And that fulfills that quota to 100%. So that's because what happens is you have this constant refraction situation going on where it will just reflect back and forth, and then in the end, ultimately, all the photons, all the light will go towards the very right detector.
Yeah.
So we don't want that.
Well, what if we did that, and we put it? What if we did it how it was, and we put it one square to the right?
And we put this one here.
Yeah.
That would then come out at an angle.
But everything shifted. Everything shifted to the right. Yeah.
To the right. Yeah, that would work. Or would it?
Let's try it.
Right.
The rock says it's tricky, isn't it?
Oh.
Wait, that didn't do any.
So what if I rearrange this? Nope. So I think
If anyone who's watching knows the solution, help us out in the comments.
out. Let's think about this logically then.
Okay.
So we need to get 50% to the very right.
Yeah.
Which means that we want the intensity to half. Which means we can either have this facing in any direction, any rotation except for completely horizontal.
Yeah. Okay.
We want to get 25% of the light to the top detector.
Yeah.
Which means we want it to be passing through two of these surfaces, two of these glass non-polarizing beam splitters. If that's the case, how about we try? That's not going to work.
I was much more optimistic about this way, and then setting the setting that one to be flat, the top one to be flat.
Yeah, would that work?
It does have to go to every detector anyways. But how is it that 0 is coming to the top? That doesn't make any sense.
No, it's
going to the top. Okay, now we're kind of close, right? Oh, because it is going to the bottom.
Oh, interesting. Except it doesn't go to the very bottom. Oh, it does. Oh, you just have to give it time.
Okay. Yeah. You can fast forward it.
Oh, we did it.
So we did 50. We did exactly what we were supposed to do. Okay, is it possible to stop here and then see and then look at what we did? Yeah, go back. Yeah. Does it make sense?
It does make sense, actually. We have 50%. So I guess this, not every photon will go up or down, but every photon will either go up or down. So there's that binary choice. However, there is a greater probability, there's a 25% probability of it going up into this top detector than it does in the bottom detector.
The way I read that first slanted one is that it's either going to go right or it's going to go up.
Exactly.
Yeah. Okay.
So we should have the light either going, if we ignored this completely horizontal non-polarizing beam splitter, then we'd have 50 and 50 going right and down.
Yeah.
However,
50.
50
goes right and 50 goes up.
So if I show, actually no, sorry, up, yeah.
Yeah, 50 goes right, 50 goes up, and then of that 50 going up, we're actually reflecting 50 of it down.
Exactly.
25. But then of that 25, 12.5 is then going maybe left, and 12.5 is getting through down.
Exactly.
Wow, I wonder if this is useful for anything.
I'm sure it is, and I'm sure in quantum experiments and in actual, situations where you've got to reflect light in certain ways,
you've
got to use these kinds of tactics to reflect light and calculate their probabilities to be able to get them at the right. I would say concentrations, but it should be intensity, at the right intensities.
Okay.
So,
if it's a wave or a particle, does that change the terminology that you use, like intensity?
It shouldn't do.
Okay.
Well, okay, I guess intensity can be thought of more as a wave-like property, so it's more of a classical concept, but I'm sure you can have intensity, the quantum concept. I can actually search that up. Light intensity. I'm
'Cause
pretty
we're,
sure.
we're counting the number of photons here.
Yeah.
Hmm.
So, if I show you an equation of intensity.
Oh yeah, change your tab, your
Yeah.
share.
Hang on, let me change the tab that I'm sharing.
To everyone that's joined, we're playing a quantum computing simulation game.
Yes,
Bonnie's just so cute.
oh, the game is very cute.
So how do we measure intensity?
So, let's see. I'm just pulling up some random. Here we go. This looks familiar. So intensity is luminosity divided by 4 pi diameter square. I'm not sure. I'm not convinced about that. Right.
Number of photons divided by time and area.
Yes. So that is one of the equations for intensity.
Oh, okay.
So that the equations are slightly different, but ultimately they should be proportional to the number of photons, because the number of photons is also proportional to the energy that we have. So if you see here, in classical physics, we express intensity as energy divided by time times area, but in quantum, light intensity here is number of photons over the time times area. So if you've got those equations and both of them are light intensity, then you know that your energy is basically proportional to your number of photons, which makes sense because photons all have an energy, right? So when they are incident upon any surface and they hit that surface, they're going to hit it with a certain energy, or even, they start to promote electrons on that surface, and that's called the photoelectric effect.
How much energy do they have?
Photons?
One photon.
One photon. It depends on their speed and their momentum.
Oh, it depends on the speed and the momentum. Okay.
Photon energy. It should be equal to HF.
Momentum is just mass and speed, right? Or does that not apply for? Does that apply for photons as well?
Yes, in the classical form, it does.
Okay.
Yeah. So here we've got. Here we go. This is exactly what I mean. Energy of a photon is pretty very standard equation.
Oh.
Energy is Planck's constant, which is a constant that was worked out, times the frequency, which is equivalent to Planck's constant times the speed of light over the wavelength. So frequency is speed of light divided by wavelength. The way this was worked out was using a classical, or rather, this was worked out through rearranging all these equations. Let me actually look for it.
So the speed of the photon isn't actually changing.
The speed of the photon, if that changes, your momentum would change.
But isn't it going at the speed of light?
Typically, yes, but in different media, it can slow down.
Okay.
So, yes, that's why we assume that if a photon travels at the speed of light, then yes, you will always have your speed of light divided by your wavelength as the frequency.
Mm-hmm.
To find, oh gosh, hold on, I've just clicked on a different. To find your momentum of a photon, which is p, here you have the energy divided by the speed of light.
Got it.
That's the kind of baseline standard equation. Here, that's where we get Planck's constant.
Planck's constant divided by the wavelength.
Yes, exactly, is the momentum of a photon. So Planck's constant was derived by multiplying this momentum by the wavelength.
Where does it get its wavelength from?
The wavelength of a photon is determined by kind of, if you look at the photoelectric effect, or rather maybe the double slit experiment, you can see this kind of fringe pattern. So if I write double slit experiment, here you've got all these photons that accumulate at certain distances from each other when they pass through the double slit. So that kind of shows their wave-like nature. But at the same time, we know that these are photons. So when they accumulate at these fringes, you've got a distance between them, and that there is your wavelength.
Oh, but a different photon can have different wavelengths or the same?
Yeah. Well, they would have a constant. Can different photons have different wavelengths? I think different colored photons would have different. So different colored photons have different wavelengths because they're. Yeah.
Yeah. Of course, yeah. I was thinking of electron for some reason, but it says of course, an X-ray photon would have more energy than a visible light. If they didn't have different wavelengths, then we would just be seeing just one color, you know?
Exactly.
Okay. Sorry for all of the questions.
Yeah, exactly. No, did you say sorry? No.
Questions.
This is good. So we've got varying wavelengths depending on the electromagnetic spectrum. So this is like high school physics, basically, where you've got different wavelengths for different energies, different waves of different energies, different, I guess, different particles, X-ray photons, gamma ray photons, visible light, etc. And that determines the color.
Okay.
So, yeah.
Got it. Well, thanks for the little lesson.
Some basic physics. It's good fun.
Yeah. What's our next challenge?
Let's see. I'm just going to open it up. There we go. Okay, so let's go back to our level map.
Uh-huh.
We've got 10 and 11 unlocked.
Oh, we're past geometry now.
We're past geometry. We're now on quantum interference. So this is introducing interference.
Okay.
All right. Let's figure it out. Interference. So this is actually ties in really nicely with the concepts that we're talking about to do with the double slit experiment. And that's an interference pattern ultimately. So let's see. Once again, we need to reflect these off the mirrors, and the glass beam splitters are going to send 50% one way, 50% the other.
So I have a feeling that they interfere with each other. Is it when they cross paths, or is it when they are split, or both?
Oh, you mean photons?
Yeah, in this case, it has to do something that's not classical, right? It has to do something strange.
Yes. We're going to need to move these two mirrors to try to identify how to reflect these correctly.
Okay.
So I think now this photon should hit the first beam splitter, mirror, beam splitter, mirror, mirror, beam splitter. Ooh, is this going to work?
So it starts on the left, and then in that first blue one, it gets split into two. Then they come back together. Then the two halves, the two split parts, they come back together. Right?
Yes. You mean? Let's have a look. Yeah, exactly. So they come back together. They hit this bottom one. Then we need to now make sure that we capture.
Wait, but that's crazy because aren't they supposed to split apart at that bottom one? But instead they're joined back together.
They join back together because of the two mirrors on either side. So they're split here. The two mirrors then receive these two photons, gets reflected off, hits this other beam splitter. Now here, actually, yeah, that's an interesting.
Right? That's not what you'd expect from the past level. You'd expect it to go in every direction. Right?
That's interesting.
Something spooky going on here.
Something spooky. So that's interference, I think.
Must be.
So what goes on is you've got you've got 50% going one way, 50% coming from the other way. When they interfere, because they're interfering kind of at reflective, I don't know how to describe it, but like the same thing, and they kind of crash into each other, the same angle, but from either side of the beam splitter. So this, then they come together and they move as one, so they kind of merge. Then they get split again by this other beam splitter. Where do they go? They're going to go either way.
Into the bombs, of course.
They cannot hit these mines. We will die. So we need to prevent that from happening. And we need to place some mirrors there. Now, that should work nicely.
There's a couple of questions from the audience. Well, Bonnie says perfect mini physics launch lecture.
Oh.
But
funny.
Naveed says, why do we want to have the photons detected by the receptors in the first place?
Why do we want, do you mean the detectors?
Why do we want to have the photons detected by the
detectors? That's a good question. So often in experiments, we want to see if there is, if there's light, or if there is some kind of energy. If you want to measure the energy of a certain photon, a certain like incident light or something, like you want to measure, you could probably even measure the, I don't know, I'm just trying to think off the top of my head, you can measure the radiation, if it's like a more polarizing kind of, not polarizing, but if you've got photons like X-ray photons or gamma ray photons, you can detect that a photon is present. You can detect, you want them to arrive at the detectors.
Yeah.
I guess another thing is you can prove quantum mechanics.
Right.
And you can prove interference effects.
And also in a more general sense, like I know a quantum computer might not use these detectors, but you could, if you were doing running a quantum algorithm, then these detectors would be how you would calculate the final result of whatever you were doing, right?
Exactly. And also things like these detectors, say you have an X-ray machine, you want to diagnose a patient and you want to see the structure of something, you can actually use photons. And those X-ray photons are in those X-ray machines, and they have detectors that will then show you where the light gets blocked and where it doesn't. So in a way, that's a similar kind of concept.
But this is just a game, Naveed, so...
This is, this is just for fun.
Skills.
Good questions, though. It gets you to think about the real-life applications of things, and I think that's always that's a very exciting part about science, about physics. All right, so I think...
Oh, you did it already. Okay.
I think we've already done this one now. Let me speed it up.
Okay, so this one is very interesting because basically when you split them, when it goes through the beam splitter, it looks like two separate photons, but actually those are entangled. The one that's going right and the one that's going down, those are
I wouldn't say entangled, but they basically get split by the non-polarizing beam splitter, and then they will collide in a way. They will interfere, is the correct.
Okay, so that's not quantum entanglement.
No, so not quite. So quantum entanglement is when you talk about spin. So I think we're going to get to that later on in the game.
This is just directions.
Yeah.
This is literally just the direction that it's traveling in. But then why, if one's going right and one's going down, why does the resulting one go? Oh, it goes right because of the way that the beam splitter is facing?
Oh, you mean at which part? Oh, yes. Yeah, exactly.
Because the one coming from the top will have a right-facing component and an up-facing component, and the one coming from the side will have a right-facing component and a down-facing component. And so somehow the up and down components cancel each other out.
Exactly. So because the initial energy or the momentum of this photon is to the right of the grid, then that is going to translate into those two photons that the single photon gets split to. And then again, both of those still have that right component, and that therefore it goes to the right. Because the energy is to the right.
It's all about energy. Okay, I was getting really ahead of
Energy.
the entanglement.
Yeah. Entanglement, I'm sure that will come up in a bit.
That's what I'm waiting for.
Yeah, that's the exciting bit. All right, so next level.
Okay.
Hee hee hee. That's the one annotation they have. Okay, so what's the goal here? Smash it. Let's smash it. I'm guessing we have to smash the rock.
Really?
I'm not sure. Maybe not. Maybe it's just there.
So what do we think will happen? I think it looks fine actually, because you know what I mean?
Also think it would look fine.
Okay. Oh no.
Ah, okay. Because there's only a downward component, that's the issue. We need to get a quarter of this light to go right. How are we going to do that? I reckon we're going to have to use this rock to block the light.
I have a question. If you click on the beam splitter,
yeah,
if you like get that window, you see they have this this map on the right side. It's really confusing. But
I agree.
But I think this has something to do with what we're seeing, like, because you see there at the very top it goes right, up, left, down.
Yes. Yeah. I do see that.
So if it's going right, if the input is right, then the output.
It's like a matrix of the different possible outputs from the certain inputs that you get. So in this case, our incident photon is coming from the top. So I'm guessing it's this final section here.
It's coming from the top.
Coming from the top, so it's going downwards. So we're probably looking at the final two columns and final two rows. Oh no, sorry, final two columns. The output here is going to be, what does this mean? Phase 0.25 tau. And this is going to be 0.25 minus 0.25 tau upwards. Right, so we've got phases here. Interesting. Okay. And I'm guessing this diagonal represents the actual beam splitter.
Uh-huh.
Not sure.
Well, the diagonal is the part. It looks like the diagonal is the part that's going through. Like the green ones is the part that's going straight through, and then the other colors are the part that's getting pushed off to the side, if you know what I mean.
I think so.
Wow.
I think so. It would be good if they had an actual explanation behind this. It would help a little bit. It's a matrix operator. Okay, interesting. Change basis. You can also change the basis. Ooh.
Oh wait, what happens if you do that?
Oh.
Is that perhaps
spin?
Rotating? Is that the same as rotating it? I'm not sure.
I wonder what that is. Oh, I see. Okay. Oh, interesting.
You understand this?
Very, very mildly, but not quite. I feel like the logic it's to do with the up and down spins, or the kind of, this is directional, so this is probably to do with coordinates, like XY coordinates. That's the first side, kind of horizontal and vertical arrows. This is probably to do with a 45-degree angle. So this one I'm not too sure about. I'm not too sure about the middle one. The final one, I'm guessing, is probably spin, the spin basis. But they're different kinds of quantum basis, I think.
Oh, okay.
So I wish it had an explanation, because right now, with my rusty
Oh, right.
uni physics knowledge, I can't remember exactly why this middle one would occur, and I can't. Yeah. Interesting. Okay.
Okay. We'll come back to this.
We will come back to this, and I'll provide an answer on that at some point. This is a good good refresher on physics. Right.
Hey, did your lights go out?
Yeah, I'm actually very dark. Give me a second.
Do you want to turn those
I realize that it's very dark. Give me one moment. Let me.
on? Okay, I think we're gonna get this one.
Right. So sometimes you don't realize that the sun has already set. It's daytime all until it's about 8:30, and now the sun is starting to set a little bit earlier here in the UK. So there we go. Let's go back to this. Okay.
This
So
looks great. Yeah. Easy.
Oh, okay. There we go. We just have to interrupt it with a rock. But now the probabilities of them reaching each
Should be equal.
should be equal, so it should hit the quota. But somehow it's not.
We're seeing a little bit. I think we're just seeing some noise here, don't you?
It could be.
One's at 20, one's at 30%. Yeah.
You're right. You're right. So that's due to the fluctuations and the random probabilistic nature of the photons either going right or down. Cool. Redirecting light. Okay. What is this? This is new. And the rock says it's easier than to redirect a river. I agree.
So higher.
Right, here we're talking about refraction. So a higher refractive index makes light slower. We set its thickness so that it retards the phase by λ/4, which is basically quarter wavelength. I'm just going to say quarter wavelength. Useful. Yeah, useful for.
So it always slows down, retards the phase by a proportion of the wavelength.
Yes. Well, in this case, yes.
Okay.
Yes, and that's dependent on the thickness of the material that you've got and the material itself.
Wait, so is the phase the wavelength?
Yes. So the phase is your change in the wavelength.
Uh-huh. Okay.
So, well, it depends on if you want me to show you like a...
Yeah, actually I need to understand
All right.
the relationship between phase and wavelength for this.
So phase, one sec. Phase of a wave. All right, so here what we have is the phase of a wave. Here's the wave.
Mm-hmm.
And what we have is a phase difference. So
Right.
these waves are a certain amount out of phase. I suppose the best way to explain this is probably using... Oh, actually, this is a pretty easy diagram. All right, in phase, we actually have two waves that are superimposed on top of each other. That means they're completely in sync, in phase. Out of phase means that they're slightly off. They're just off. They're not superimposed on top of each other. They don't have the same phase, the same kind of heartbeat, I guess.
There must be an example of this with sound, right?
Exactly. So interference occurs when waves are out of phase, and you'll get different levels of interference dependent on how out of phase two waves are. So when they're completely out of phase, like this bottom case, we've got the pink and blue, they're completely the opposite of each other. What would happen here is that you will get a complete cancellation of the waves. So it will just average out to zero.
Yeah.
Yep. And as you can see here, this is a very similar... Actually, this is a visual representation of what's going on in our quantum flytrap.
Uh-huh.
So here, they're a quarter of a wavelength out of phase.
Got it.
Which means they're just that quarter out. So from the peak till 0, or rather, this part is the trough, it's the bottom. But it's just that quarter wavelength out of phase.
So if we took two photons,
Yeah.
and then we took one to be 1/2 out of phase, and then we collided them back into each other.
If they're half out of phase,
If they're not photons but streams of light, would they then cancel each other out?
yes, exactly. If they're the same frequency and
Uh-huh.
the same wavelength, yeah.
Okay. Well, then what would happen to the photons? They wouldn't go away.
No, the photons would destructively interfere.
Okay.
So when you're looking at the double slit experiment, where you see these bright and dark fringes, like here, or maybe, yeah, okay, sure,
Mhm.
this works, or the image I showed earlier. These peaks are where the photons are landing. So
Yeah.
that is where you actually have the photons completely in phase. And then when they're completely out of phase is where you see absolutely nothing, because they cancel each other out.
Yeah. Okay.
So there we go. There's your physics.
Okay. I feel ready for this.
Cool. Right. So in this case, glass has a refractive index of around 1.5, meaning that light travels at a slower speed, which is equivalent to 2/3 of the speed of light.
Okay. So when it goes through the glass, is that going to change just the phase, or the wavelength doesn't it doesn't change the color of the light, right? The wavelength, right? It just changes the phase.
Yeah, exactly. It wouldn't change the actual wavelength itself or the frequency, but it
Okay.
would change the phase. Yes.
Okay. Cool. Got it.
Cool. All right, let's do this. So we are trying to redirect this light. Let's see what it does initially.
Mhm.
Now, actually, you can tell that we're going to need to shift this by some kind of phase because
Why?
this setup already, you can see that there are the difference between this top mirror and this beam splitter is 3 across, or rather, there's a gap of 2, so it's about 4 across.
Oh.
Across here, it's actually 6 across. So actually, they're already kind of, you have to compensate for that.
The interference we were seeing before, it only works if. Oh.
I wonder if that's going to work.
Actually, but I don't understand because the distance is still the same between. What would happen if we do it without the glass?
Well, let's have a look. We're going to get a lot more light in one direction than we are in the other. So we can. Oh no. So basically, it doesn't go upwards.
All of it's going to the right.
All of it's going to the right, which means we must have to change it by a phase factor. So let's have a look now. If we change it,
Yeah.
does that work?
Still going to the right.
So I think I need to change this.
What if you just change one?
Maybe.
Now it's 50-50.
Now it's 50-50. So we want, what did we want? We want nothing in the top one.
Okay.
Everything in the bottom one. Sorry, we want nothing in the right one and everything in the top one.
Yeah.
Not saying the right words. There we go.
I have to admit, I don't actually understand what's happening here.
So here, what we've got is these two glass. What are they called again?
The thing I don't understand is why it doesn't split them up from the beginning. Why are they interfering in the first place? How can we see that?
How can we see this initial split?
That they're all going to go to the right instead of going up.
Well, again, like our previous example where we had the initial component being in the x direction, so as in to the right, these photons are originating, pointing from left to right, so they're traveling from left to right.
Yeah.
That's initial energy. So therefore, we have that horizontal component going to the right, so therefore the incident photon's going to go to the right in the end. Just like our example where we have the interference. We had one of the levels which had the photons merging.
Can you show the matrix operator chart again for
for the beam splitter?
So it splits it up into 2 phases. Oh. So like, okay. So it looks like it's splitting it. If you would just take one and put it through the beam splitter, it looks like it's splitting it into 2 of the same thing, but it's actually splitting it into 2 photons of different phases.
You mean when we have the beam splitter?
Because here, like, it gets split into, if it's coming from the left side,
Yeah.
It'll get split into green and blue, right? Or orange and green, and those are different phases.
Yes. Yeah. I thought it was orange and blue, and it gets split into. Actually, I'm not entirely sure.
But so, if it's coming from the left, then isn't that horizontal? What? Oh no, because there's
If it's coming from the left, you'll get the vertical. You'll have a component that is that's going from the left to the right. As in, it's traveling right, coming from the left, but it's traveling right initially. So that's why we have that vertical component. When it hits the beam, it's going to be split into an upwards and a right component, and then again it converges. So it splits into now a right component and an upwards component, and when it meets, it will have that original right component when they interfere.
Yeah, and basically the components of the same phase, they don't interfere, but the ones of different phases, they interfere, right?
Well, in this case, they constructively interfere. So because you have this 50% from the mirrors, from each of the mirrors, they're going to sum up to 100% when they constructively interfere.
Okay.
When they destructively interfere, we're going to have some cancellation.
Right.
So when we shift them slightly out of phase, we notice that we actually have a little bit less in one direction than we do in the other. So now this, if I pause it, this bottom right photon, or actually 50% of that photon, I guess, that then passes through, it becomes a quarter of a wavelength out of phase with the other one. So we notice that we're going to see only some of the photon go upwards and some to the right. So we have 50-50 in each, if that makes sense. If they're just like the diagram that I showed. Oh no, I got rid of it. One sec.
Yeah, I remember. So you have basically this. Yeah.
They're going to be just a quarter wavelength out of phase. So you're only going to see 50% of the light. I want to find a better example where they're superimposed. Maybe here. That looks about a quarter out of phase. If you average this, it's going to be half the intensity at both ends, both plus and minus a half, if that makes sense.
Yeah, and I remember something about if it's 1/8 out of phase, then that's when it starts to get kind of weird. Do you remember this?
When it's 1/8 out of phase?
Or
when it's 1/8 out of phase, you will probably only see. Oh yes, there was that weird.
Right? You expect that you would see like in between. It's more than you would expect.
It would be, yeah, you would kind of expect there to be either greater than 50 or less, so it would be plus or minus maybe 75% of the intensity on both sides. I'm not sure. That might be a completely wrong estimate of the calculation, but that would equate to like a 90 degrees phase shift.
I'll find what I was thinking about and send it to you.
All right, cool. No, I think I know what you mean, and I think that's just because at the certain spots that you observe, you can observe more extremities or greater differences in the two waves. But yeah, I guess we have to explain that properly.
Yeah.
Let's continue.
Okay.
So here, if I go back to this and I start playing this, speed it up. Ta-da!
Good.
Great. Does that make sense?
Interference. Constructive interference.
Yes, constructive, destructive, all of that good stuff. Split so you can join. Okay, interesting. We want to get 100% of the light into this detector.
Oh, wow.
All right. Let's see what it does without any help. All right, so half of it, some of it hits the rock.
Yeah.
We don't need it to hit the rock. So we want to move these mirrors so that it doesn't hit the rock. I wonder if we can just split it all along the way.
That looks good.
I wonder.
Whoa.
Does that make sense?
That's really cool.
Yeah, it is. The way that this proves our interference logic, where you have this initial energy that's to the right, and when it meets the beam splitter, it's going to diverge into a 50-50 kind of ratio, and then it's going to converge at the next beam splitter, and then it will keep moving in the initial direction of travel, and then it will meet at the next beam splitter, where it will then move again. It will just keep moving in the direction of travel.
So that energy stays, so the total energy stays the same?
Exactly, yeah.
Okay.
Energy must be conserved. There we go.
Splitting doesn't change the energy.
No.
Doesn't redirect the energy. No.
It will change the energy per branch that it's split off into, but when it converges, it will come back to the same energy.
Got it.
Peaking at a photon. Interesting. Okay. So here, we could actually, before I even started this, we could predict that it was going to go just to the right detector. What is this? Peaking at a photon and its consequences. Okay, here we have a non-demolition photon detector, which is a non-destructive, direction-intensive photon measurement with 100% efficiency. Okay. Interesting.
So we're measuring it's a non-destructive, direction-insensitive photon measurement. Oh, so that means that we can measure a photon coming in from any direction.
Yes, and we won't affect it. We won't affect its course of travel or any measurements. That's so interesting. Oh.
Is that allowed in physics?
I guess it's the concept of observing a photon. That's what we're talking about. It's like when you make a measurement and you observe something without actually detecting it.
But are we getting what aspect of it are we detecting? Just that it exists?
Yes. Exactly. I think so. From my interpretation, I think so. Let's have a look. So this one is all going to go to the right photon detector, which we don't want. So what are we going to have to do? This detection.
So this is very quantum because we are just observing something and that's supposed to change it.
Yes, exactly. I'm wondering if it has... Oh, that's so interesting.
What happened?
Okay, this is very quantum. Right, you're very right. When we make an observation of a photon, sometimes we change the outcome. And I think that's the point it's trying to illustrate. This is very interesting. All right. Should we speed this up and see how it goes?
Wait, so what happens if we don't put in that
If
observation?
we don't put in this observation, then it's going to all of the light is going to be detected towards this right detector, because that's how its initial energy was directed. It was directed to the right. So we would see the photon diverge, converge, and then hit the right detector, which is not what we want.
Wait, so why does observing it make it go down?
So when you make a measurement, well, when you make an observation,
Yeah.
sometimes it can change, and that's just a very quantum phenomena.
So there's something about if you isn't there something about if you observe the position, you'll change the momentum, or the other way around?
So if you observe the position of a photon, you can't observe the momentum.
And observe the momentum.
If you observe the momentum, you can't observe the position.
So we observed the position, which caused the momentum to be 50-50, or no?
Yeah, it kind of collapsed. I guess the wave function collapsed on itself.
Because we observed the position, therefore we didn't know which direction it was going to go anymore.
Exactly. So its momentum became unpredictable or unknowable.
We collapsed the wave function. We've done it.
Yes, we've done it. What I can share is Heisenberg's uncertainty principle, which states that you have this inequality here, which states that if you make an observation in the momentum, you can't make an observation. You can't get the position, and vice versa. And if you factor in, well, actually, yeah, this is the Heisenberg uncertainty principle. Is you've got position, which is x, and this or chi, I guess in this case. So delta chi, delta rho is the momentum. So that factored or that producted is then greater than or equal to, this is h bar over 2 is Planck's constant over 2 pi. So
what does the operator mean here?
So we've got the uncertainty in the position, which is delta x, and then delta p, it usually is delta p, is greater than or equal to h over 4 pi. In physics, we just like to say h bar, which is h over 2 pi.
Yeah.
So the more accurately you know the position, the less you know the momentum. It's basically a constant. So the change in position times the change in momentum is always going to be h bar over 2. So you can only have more of one or more of the other.
Akhilesh commented, he got it already. He said something about the observation that changes the momentum. Indeed.
Oh, nice.
We have a physics expert here.
Physics expert in the chat. That is great. Great. You can teach me something about
Maybe
this.
the chat can help us to get through the next level.
I think so. Let's do this. All right. Here we go. So here we want to, well, here we can already see that this beam splitter is going to split it 50% one way and 50% the other way. So let's see what it does without doing anything to it. Ooh.
Oh yeah, we've seen this.
Yeah, we've seen this. So this is the Mach-Sender interferometer. I think it's a simulation of that. It's very interesting.
Interferometer.
Oh, okay. Right, we didn't have to do anything.
We go back. That's not fair. Can we move? Oh wait, did we move something, or was this?
We didn't move anything.
Okay.
So I guess it was set up for us, but we can play around. And the point of this is to illustrate that the Mach-Sender interferometer. Okay, so we got that in 11 clicks. It's just a setup for a Mach-Sender interferometer. You've got two different two different sides, two different arms of the interferometer. I might pull up like a. Let me see if I can find the diagram.
So you have these two mirrors at the end of each arm, at the end of the arm.
Exactly. And this is a very classic, like very typical setup. So here we've got a laser at the end, you've got a beam splitter, you've got a sample, you've got, yeah, so this is exactly what we're seeing in our quantum flytrap. You've got two detectors. Oh, in this case, you've got two detectors, all right. Or you can have something like this.
Okay, a beam splitter, two mirrors. The main point is that they come back together.
Exactly. So it's a way to prove destructive or constructive interference depending on which detector you look at. Let's go back.
Oh, because we could have two detectors here, right? Here we just have one, but we could have two.
Yes, exactly. We could.
So, and that one would be at the bottom. If we'd have another detector, that one would be on the bottom.
Oh, well, in this case...
But we do have a detector on the bottom.
We have one detector. We have one detector in our case.
Check it. The red triangle is also counting. I just realized.
Oh.
Or is it?
Weird.
Oh, no, maybe that's just how much...
No, that's the clicks. That's the number of clicks.
Oh, never mind. Okay, yeah.
Yeah. Interesting.
What would you use one of these things for in the lab?
Interferometer?
Yeah.
I guess to observe destructive and constructive interference.
Okay.
Or like when you have different samples, different kind of crystallographic structures, different crystals, then you might want to measure the distance of the atomic spacing of the crystals. So you might be able to pass them through a Mach center interferometer, if I remember correctly, unless I'm talking absolute garbage. But I can search up applications just to make sure. Aerodynamics in plasma physics and in heat transfer to measure the pressure, density, and temperature changes in gases. Cool. And they're also used in electro-optic modulators, electronic devices, various fiber optic communication applications. So yeah, it's used to work out to transmit light and photons.
Okay. Oculus says he's not an expert, but did you take quantum physics?
Me?
No, I know you did.
Oh.
Right? But
yeah, I did.
But I was wondering if Oculus did.
Oh.
Okay. I didn't know that. What's next?
All right,
I think we can do one more before my brain explodes.
Yes, sounds good. Sounds great. All right, here we go. Let's go. So, wow. All right, this is a good one to finish on. Number 16. So here we have 3 detectors. We also have a mine, so we have to be really careful of that, because if that explodes, we die. So let's see the trajectory first. Okay, that looks good. So it seems like this will all be directed towards the bottom detector here, which we don't want.
Mm-hmm.
We want only 12% to be detected at this bottom detector, 12% at the very right, and 50% at the very left. All right, so how are we going to do this? We want to use one of these 3 items, or maybe all, either the rock, which will block the intensity in a certain direction, the glass, which in this case is actually half a wavelength out of phase. Half a wavelength will mean that it will probably cause destructive interference.
Mm-hmm.
And you've got this non-demolition photon detector. All right, which means when you make an observation, the measurement changes. How are we going to do this?
And when we put that in the path of the photon, it makes it so the momentum is no longer predetermined.
Exactly.
But it does that for both. Does it do that for both splits, both sides of the split? Right?
This.
It does it
Yeah.
for both sides, because otherwise it wouldn't be it wouldn't sum to this. It wouldn't balance out, would it?
Let's see. So, I wonder. I don't actually know. Nope. All right, I've chosen a completely useless location.
So just put it somewhere in the path.
Right. So, actually, can we pause for 2 seconds? I just need to do something.
Yeah, sure, no problem. I'll
Yeah.
be staring at it.
Okay, cool. Or you can take over if you want.
Yeah. Okay. So, the point of this game is to get the right amounts of photons in each of the detectors. This is the most challenging level that we've had so far. So we're gonna have to end up with 50% on the left side, 12% on the bottom, and 12% on the right side, which means that 25% will also get thrown away. So, it's going to come out of the light source in the top left corner. Then from there, it will be split, going right and down into the mirrors. From those mirrors, it should come back together. And then I believe it would continue on to the right. It would be split again, up and to the right. Then from there, the photons would bounce back to left and down.
Right, I'm back.
I've worked my way through the first part of it. Can you play it again so I can check my
Yeah?
check my mental working? Just exactly. Okay, I just got to the first half of it, and it did what I was thinking it would do. Here we have some thoughts from Avi, who is a YouTube student of physics.
Oh, amazing. Very cool.
I know him. He studied computer science. That's why I was wondering if he studied physics.
Oh, brilliant. Do you have
Um,
any physics modules or something?
He says he just learns on YouTube, but
Very cool.
he has some ideas.
Can you put the rock
We
at
can
the
test it out.
somewhere? The glass at the left bottom and the observer in the middle somewhere. All right. So the rock. I was thinking something along those lines as well until I got sidetracked. No. Okay. So we should be careful of the mine. We have to be careful about where we place this rock as well. So
We need to use the rock, the glass, and the observer.
yes,
Oh,
absolutely. So let's trace this through. We probably want to put the rock. Let's replay this again. So beam splitter, light splits 50-50, light converges. It's going to hit the second beam splitter, which is then going to reflect off. We now want. Okay,
then it splits again.
It splits again. We probably want it to split a bit before that.
Because now it should all go to the right. Isn't that what it would do now?
Yes.
Okay. Akhilesh, Akhilesh asked, what does the glass do again? It changes the phase, which changes the behavior when they interfere.
Yes, absolutely.
Yeah.
In this case, what it does is it changes it by a phase of half a wavelength. And that means that it is going to be completely out of phase which means if without this glass, if the end state was to go to this bottom detector, instead of going downwards, it's going to have so instead of having a vertical motion, it's going to have a horizontal motion. So if I place it here, you will notice that actually all the light will go to the right detector rather than the bottom detector. So it will go along the x-axis, not the y-axis, because it will be half a wavelength out of phase. That makes sense? I hope that does.
Yeah, he says, got it.
Awesome. Cool. All right, so now that we know that, we know how to get it to the right detector, but we want it to be 50-50 at the end of the day towards the right and bottom detectors. So what we want to do is probably place this glass phase shifter somewhere else, a bit earlier on in the flow. I wonder what would happen if we placed it here.
Won't that just cancel everything out? No.
No.
Because it's only on the...
Doesn't do anything. I don't think that's useful. Maybe here. That's not going to work.
Wait, but that did change it, right?
That did not change it. So
What is it doing without the glass?
It goes all the way to the bottom detector.
Everything goes to the bottom detector?
Yes.
Oh.
Yeah. So when we have the glass, everything will go to the right detector. But we want it to be 50-50, so we want it probably further closer in the flow.
Oh.
Not too close.
We're all dead.
Maybe if we block that.
That seems too easy.
Oh, well, let's not underestimate it.
But I'm down with it. What if you put the
Oh, but only the
if you put the glass, what if you put the glass into one of the arms of the that German interferometer thing?
Maxenza interferometer?
Yeah, what if you put it in the that on the top right? That's kind of similar to that, right?
Yeah, you're right.
So my thinking is
it doesn't do anything because
why?
All right, let's see why. Nothing happens because if we think about how this light flows, right, they meet at this point 100% of its intensity. Now it's going to split.
Oh, because it changes shifts it twice.
Yes.
It gets shifted fully. Yeah.
Exactly. So when it shifts twice, it shifts a whole wavelength out of phase, which ultimately is still the same thing.
Pointless.
It's pointless, yeah, exactly. Exactly. So we only want to shift the phase once, in which case I'm wondering if we can put it somewhere in the path a bit earlier. Oh, that's dangerous.
What about, I think we already tried putting it in the bottom right corner, didn't we?
We might have.
Like towards the bottom right side when it's about to go.
Here?
No. We need like chessboard names.
Chessboard names, we do. This should have coordinates. That's my suggestion to this game. Have coordinates. Or like an axis.
Yeah, I want it to go like in the path. Yeah, like no, just down to, yeah, something like this. I thought we tried this already.
Did, and it went all the way to the right.
Oh yeah, okay, that's great. That makes sense.
Yeah. So what we want is probably somewhere earlier in the trajectory of this. So I'm thinking, what if we put this somewhere here? Except now it's just going to go to the mine, which we don't want. I wonder if this would work.
Okay.
Oh no.
You got lucky there, but
I got lucky there, but I guess what we have to do is...
Would this work?
Would it?
Try it.
I don't think it would get the entire flow.
Well, it looks like it's getting half of it.
Yes, but it's not getting the
But that's
the
okay, right?
But we need some of the photons to go to the right detector.
I missed those. Yeah, putting it too early disrupts the whole flow.
Exactly.
So
So
put it there.
it's not going to hit that area. I'm wondering, what if we put it here?
Okay, we have 4 people watching in the comments. Someone's got to know the answer to this one.
Someone let us know.
Physicists.
Unless I think we might have to place this black box a bit earlier. Oh, that's interesting.
Okay, but the rock is if you put the black box earlier, you're gonna get things going all over the place, won't you?
Yes, it's true.
So
Oh, hang on. Maybe we should place this closer to the Mach Zehnder interferometer. Hang on. Let's see. Oh, interesting. Not quite what we want. Maybe.
I feel like that one should be near the end, but that's just my feeling.
The black box?
That was just my feeling that it should be near the end.
Could be. Could be. We could put it here.
If it's near the beginning, then basically
Actually, that would work.
use the phase. Actually, if you use the glass after the
rock.
After the observer, won't it just do nothing? Because it at that point, I don't know what I'm saying. So
I think we're doing a lot of trial and error here.
Yeah, this is complex.
Right, maybe let's think about this rationally. So we want 50% in the very, very left detector.
Yeah.
We want 12% to the very right and 12% to the very bottom.
Uh-huh.
Meaning we need to get half of the light directed, or we need to find a way of getting it directed to this bottom detector. I think once we've solved that, we can probably work on the other two, where we only need 12 on each. And we know if we work backwards.
Oh, yeah, you're thinking of going down first. Oh, why didn't I think of that?
Maybe. Or we need some kind of phase change early on so that we can split. Maybe not, but not going to work. What a dilemma.
What other places can we put it that we haven't put it yet?
Well, I guess it's the unique combination of all these three. Well, interesting. This stops getting recorded after a certain amount of time.
What does?
As in the the setup on the right-hand side is only going to the bottom detector. Is this going to work? I think we need a phase shift right before it reaches this final beam splitter, so that we can get some of the intensity, some of the photons to the very left.
Yeah.
Oh, there we go. Except,
where are the rest of them going? The rest of them are going down.
Oh, maybe it is working.
Yeah.
No, because we're not getting any photons to the very right. Oh, this is tricky.
You're actually getting. Why is it 60-40?
Not quite right.
Oh, you got 50-50.
Yes. Interesting, though.
I feel like putting the rock right before the bomb is too easy. I know I said that before, but that's my gut feeling.
No, I do. I think so. And I also don't think we even need this rock for this current setup that we have here.
I think the purpose of the rock
Is to block.
the interference.
That would make so much sense.
Right? It's
Let's
never
give it a
dead.
go. Oh, no. Okay.
Okay, where's the rest of it go? And now
No.
is absorbing a bunch of it, isn't it?
Hmm.
But the rock can absorb 25%.
Is that the rule?
Well, we have 25% left, so I was just thinking.
Probably.
Is that how it works?
Let's try.
Now the rock is absorbing 25%, isn't it? Based on where it is.
Hmm.
No.
Not sure. Unless, let's see how this sun tower. Okay, so nothing goes into the bottom right, which I think we still need to change the way that this black box works.
Oh, you can put the black box in the bottom right, which will then make it like 50-50. But
then it wouldn't quite have the same. It would not have the same trajectory towards the right-hand side, the left-hand side.
I feel like putting the black box in the beginning makes it cannot find the words, but makes it too random.
But we need something to be able to move our photons towards the left-hand side. No?
Yeah.
Otherwise, how would we get our photons to the left-hand side? This is harder than I would have thought. Or maybe we are not thinking.
How many levels? I'll check. I have the level list. We have 33 levels in total.
Oh goodness. Okay. So I think we need to work by rules. Some kind
We're
of.
going to be quantum physicists by the end of this.
We will. We absolutely will be.
Be quantum computing experts by the time
Quantum
we get
computing experts.
level 33. Quantum computer scientists.
Exactly. That's the goal. That's the dream.
Okay.
I will reinstate my my actual degree degrees knowledge. Although it wasn't quite like this, but I think this is interesting.
Well, would you like to take a break? I think we can come back to this. I'm sure when we come back to it, we'll figure it out.
We could do that.
It's up to you. It's not satisfying, but
yeah, it's definitely not satisfying. I think we're nearly there, but we can come back fresh.
I think we'll understand it better when we come back.
Yeah, I think so.
Okay, good.
All right.
Thanks for watching, everyone.
Thank you, everyone.
And
unsatisfying ending, but we'll get there, definitely.
Give it a shot at home and let us know what you come up with.
Yes.
So the website is quantumflytrap.com. So everyone can play it.
Wonderful.
All right. See you next time.
All right.
He just started and he's on level 7 already.
Brilliant.
Which took us like actually, I don't want to say, which took us more than an hour last time.
No, to be fair, we had our fair share of mini tangents.
Yeah, I mean, it's not all
explorations. It's about the.
Not all about how fast you do it, right?
No, absolutely not.
Eugenio says, "Thank you guys. Super cool puzzle game."
Oh, I'm glad you enjoyed it.
Thank you, Eugenio.
Thank you, Jenny. I enjoyed it as much as I hope you did. Yeah, it's good fun. It's good fun. And I think it's a nice way to learn physics.
And thank you, because you're amazing at this.
Me?
You're very good at this. Yeah.
Well, no, I'd like to be better, but thank you. No, thank you for hosting this. I think after I brush up on more of my physics knowledge and after I manage to solve this one, this interference problem, I think it's just a matter of trying to calculate the probabilities at each stage.
Yeah.
If you take it step by step.
Like I can visualize, I can sort of start to visualize a system of equations coming out of this. I can't write it down, but I can see how you could solve this symbolically, possibly.
I think so. I think if we were able to annotate this as well with the probabilities, that would help us a lot. And we'd get there.
We will get there next time.
All right, we'll leave that till next time.
See you next time.
Yes, thanks, guys.